Okay, so the next lecture is on diffusion flame, which will be also the topic of tomorrow. And I am not sure I will do both. I will probably only focus on half of this lecture and continue tomorrow. And so let's start with diffusion flame, some comments about this. So unlike premix flame that we spoke about yesterday primarily, where fuel and oxidizer are mixed a priori at the molecular level. So when you have a mixture, it's already, there is everywhere both fuel and oxidizer. In diffusion flame, they are separate initially, and there can be different situations that they are separate, and they mix and react only when they meet, when they get together. The classical picture or classical diffusion flame is a candle. And it's a very complex, actually, physical picture. Although it looks very nice and very sometimes nice and steady, as you see here, the reason it's complex is because it's involved fluid mechanics and many things. What you have is the wax that melts first due to some ignition or spark or match or whatever, and it start melting the wax. And if you look carefully at the bottom of the wick, you'll see like a little cup of liquid wax sitting there, and the liquid wax start getting transported by capillary effect along the wick. And so the wick now has the liquid wax. And due to the existing of the flame, the liquid wax evaporate and start diffusing out, and it meets the oxidizer outside, and a chemical reaction occur. And so you see all these descriptions that I made, probably I simplify them a little bit too, are not simple to describe, neither mathematically or in detail. In fact, I know maybe only a couple of attempts to try to simulate a candle flame. I don't know many attempts that were done, but there are few attempts to do that. And then you have also the formation of this blue flame, and due to natural convection, then the hot gases move up, and so the flame extend and have this teardrop, if you like, shape. And as I pointed out here, there are carbon particles that give the illumination and all different things, and a lot of the detail of reaction, and I don't want to get into all this. But the two important aspects that I mentioned is the fact that the fuel diffuse out and the oxidizer or the oxygen or air diffuse in, and flame get created where they meet. And if this is done under zero gravity, you get a more or less a hemisphere flame, which is purely held by diffusion, no convection that rise that give this shape here. So I mentioned that just so that to see the importance of diffusion in this problem. That's why non-premix is very often referred to as a diffusion flame. We're going to see also why mathematically in a minute. The oldest problem to describe a diffusion flame is by Burke and Schumann, and they even coined the term diffusion flame. I think I said that here. And after that, it has been referred to as a diffusion flame. They looked at a problem like this. You have two concentric cylinders. One ends here, where the fuel is coming, oxidizer is coming from the other, and then some flame get established where the fuel and oxidizer meet. And we are going to talk about this problem briefly later today. In fact, to describe this, the mathematics involve really solving here the fluid mechanics equation, and it's not trivial. And so, of course, you can do it numerically, but even then, it's not maybe totally trivial. So they have assumed that the mass flux coming out, which is equivalent to saying the velocity coming out, is constant, which is like a constant density approximation. They didn't use those words. This was later used by maybe applied mathematician who tried to simplify the equation. And if they were criticized, it's not a fair judgment, because even the big giant of combustion years before have introduced a constant density approximation in this way. Anyway, I will not start with that problem. I will start with a simpler one. In premix combustion, we said that the simpler example would be a planar flame, okay, in a one-dimensional setup. Can a diffusion flame exist in a one-dimensional setup? So in a one-dimensional setup, the mass flux has to be constant, so there is one mass flux going like this. So let's say the fuel is on the left, the oxidizer may be on the right, but if the oxidizer is convected that way, to get to the flame, it has to diffuse fast enough to reach the flame against the flow. And mathematically, this is not possible, because the equation for the oxidizer give you an exponential growth here, which cannot be accepted, and so only a constant solution can exist. If a constant solution can exist, it means the oxidizer cannot be completely consumed at the flame, as you expect in a diffusion flame. So a one-dimensional setup like this does not exist. That's important to know. So how does it exist? It exists only if you can provide or supply the oxidizer at a finite position, like here. So the first idea was in Spalding paper, and then Kirkby and Schmidt discussed that problem early on in the 60s. And they created a simple mathematical model. They say, okay, the fuel is coming from here at a velocity u, and there is a very strong stream of oxidizer on top, from which some oxidizer diffuse through, and if it diffuses through, a planar flame is established. The problem in this theoretical idea or mathematical construct is that it was immediately criticized. Well, you cannot really realize it experimentally. To be honest with you, I worked at, and now I'm introducing a little bit personal issues. I worked on that problem. And one of the importance of having a simple solution is that you can analyze perturbation of it and understand issues like instabilities. And I was at the time interested in instabilities of diffusion flames, which unfortunately I will not talk about this. I will talk about instability of premix flame, but anyway. And to start with a model like this was a nice, simple example, because as you will see, it creates a simple mathematical solution, one-dimensional, and then you can perturb it and so on. But the fact that it was criticized as being not realistic have led me to discuss this with some good experimentalists. And they say, no, we can build it. And it was built in the EPFL in Lausanne. And it is the only experiment that has been done to show that a planar, not strained, you see, diffusion flame exists, can be observed. I say not strained because most of the experiment of diffusion flame are done in a counterflow. In a counterflow, the flame is under strain, and it's a different physical condition. It's a very nice, simple experiment and simple analysis to do, and we will discuss it also here perhaps, but it's different. So the idea was to bring in the fuel through many, many tubes separated at exact distance between each other so that there is a uniformity or homogeneity, and let the oxidizers diffuse from the top. Basically what you want to ensure that when it diffuses from the top, at some distance away from the tip of those needles, or those thin tubes, they're actually needles. They use needles so that they are very thin. The conditions are uniform. So you can have a simple mathematical boundary condition at that top. And here is the reality. A planar diffusion flame was established, and this is the setup, and this is the experimental observation, and this shows you the distance in millimeter from the tip of the needle where conditions become uniform, okay? Okay, so this was just a side comment, I think a curious one. So here's the mathematical model. You have the fuel coming from the top. There is condition at this location, the green line, where the conditions are uniform. You have no fuel, you have oxidizer. Fuel is coming from the bottom. And the differential equation that described this is very similar to what we have seen before, the mass, the mass fraction of the fuel, of the oxidizer, the temperature. Everything here is known. I think in one of your versions, the new FWF was missing, but you can argue that it was embedded in some other things, but sorry for the typos. So anyway, and this is the reaction rate, and everything is as before. I just want to emphasize that in such a problem, there is an inherent symmetry in the problem. What I call fuel, you can call oxidizer, and what I call oxidizer, you can call fuel. Doesn't, of course, in physical terms is important, but mathematically doesn't matter. There's a symmetry. And so I can provide fuel here, or an oxidizer diffuses from the top, or do the reverse problem. Okay. The next thing is that I can put this in dimensionless form, and these are the equations. Not surprising, similar to what's seen before, but I want to point out the parameters. So the first one is the Dam-Kohler number, which is the ratio of the diffusion time to the flow time to the chemical reaction time, and it's inversely proportional to the velocity. So you increase the velocity of the, I will fix my attention, fuel coming from the bottom and oxidizer from the top, okay? So you increase the velocity of the fuel, you decrease the Dam-Kohler number. And there is the activation energy parameter, the stoichiometric ratio between the oxidizer and the fuel, and the heat release parameter. Okay, and then the first thing we're going to assume the Lewis number. I'm just describing how we're going to discuss the problem. So the first thing is we're going to assume a unity Lewis number. Now, if unity Lewis number, you may remember that I said that there are coupling functions. In other words, we can add, subtract the equation, whatever we need to do to eliminate the reaction term. So we can get two such relation, okay? We can also write the third one, but it's really a combination of the first two. So there are only two linearly independent, okay? There are three conserved scalar, but only two linearly independent. And it's only when the unity Lewis number. Okay, so we can solve those two or the three, which is the same, because you just apply the boundary condition and you get what this combination is. Of course, it didn't solve for the fuel, the oxidizer, and temperature separately, so we need still to solve one more equation, okay? So the coupling function essentially reduced the number of equations that need to be solved from 3 to 1, and there is only one nonlinear. Okay, well, I mean, there are two others that you solve, but they are simple. They are linear equations. Okay, now the limit of Birch-Schumann, or the idea of Birch-Schumann, although it was not introduced in this way, it's essentially that the Dam-Kohler number is infinite, is very large. It was more introduced in an ad hoc way, very nice physical insight, no question about that. In fact, you know, when you have a very strong physical insight that provide something that later is recognized as a systematic limit, it's even more impressive than otherwise. But the systematic limit is usually very useful because it allows for extending this beyond the problem that was described. So the idea is that if the Dam-Kohler number is very large, which means that the flow time is much faster, that the reaction time is much quicker than the flow time, right? It's infinite. In other words, it happened very fast, okay? Then the Dam-Kohler number infinite, if you look at the reaction rate, the only thing else that can balance it is the fact that YF times YO goes to 0. The product of fuel and oxidizer goes to 0, which in a premix flame is not possible. But in a diffusion flame, it's possible. On one side there is fuel, the other side, and no oxidizer, on the other side there's oxidizer and no fuel. So this is basically the idea that the reaction zone separates a region where the fuel is coming from here, so here there is no oxidizer, and in this region there is no fuel. Okay, so that will help a lot in the using now the coupling function, because if we take this one, for example, if we say in the region, well, first, before we even say which region is which, at the reaction zone, both are consumed, the fuel and oxidizer. So if both are consumed, this is 0, 0, 0. It gives you already an expression for the location where the reaction zone is. So the location zone is located, as you see here. And this phi, I want to comment on it briefly. It's like an equivalence ratio, but in a diffusion flame, really, there is no equivalence ratio because the mixture is not mixed up, the fuel and oxygen are not mixed a priori. But there is something that is based on the initial condition or on the condition on the fuel stream and the oxidizer stream. And so that is the ratio that I presented here. The amount of fuel in the fuel end, the amount of oxygen in the oxidizer end divided by their stoichiometric proportion. Again, if P is less than 1, it means that the system is lean, and if it's bigger than 1, the system is rich. It's not locally the flame, but it's okay. So this is one thing, and then since in this relation, since we know the location, if YO is 0, which is on the fuel side, then YF is given by this, and if YF is 0, then Y. So you see in the using unity Lewis number with the idea of Birch-Schumann that the Dam-Kohler number is infinite gives you immediately the solution for the fuel and oxidizer. What about the temperature? Well, you use a different coupling function, those two, and when YF is 0, you get the temperature. Where YO is 0, you get the temperature, and so you get the expression of temperature. And this is typically the profile. Temperature rises to some temperature, which I will refer here to the adiabatic temperature, and the concentration of the fuel go to zero, the oxidizer go to zero. The flame temperature is obtained as the value of the temperature where X is XF. So it's computed from the analysis. It is referred to the adiabatic flame temperature. I don't know if I have the comment here. Yeah, if I put it in dimensional form, it takes this form, and this is where the flame location is. So the flame temperature for unity Lewis number of diffusion flame, the flame temperature is the adiabatic flame temperature of a stoichiometric mixture consisting of this much fuel, this much oxidizer. How do I know that? This is the exact amount of fuel and oxidizer that's gonna mix at the position. If there was no combustion, that will mix at the position XF when there is no combustion. And if you take the ratio, you obtain that it's exactly the stoichiometric ratio. So that's why the condition give you to what I would refer the adiabatic flame temperature. We will see that when Lewis number is not equal to 1, the flame temperature is not necessarily the adiabatic flame temperature. We will call it the stoichiometric temperature because it's the temperature at the stoichiometric surface, and it can be above or below the adiabatic temperature. So you can have super adiabatic or sub-adiabatic temperature. Okay, so what's the conclusion for now what do you do for non-unity Lewis number? Non-unity, you cannot use the coupling function. So there are, first of all, few relations that you can establish. The first thing is you expect that the temperature and the mass fraction are all continuous, which gives you 3 relations that they are continuous at the reaction point. The second thing is that you can combine this relation to eliminate the reaction term, but note that the Lewis number appear here and not here, so that's not obviously a conserved scalar. But you can integrate this relation across the reaction zone. And when you do that, you get a relation between the fluxes away from the reaction zone and towards the reaction zone. Away, the temperature fluxes away, or conduction away to one side or another. Note that it's not necessarily equal amount of heat get conducted, and the fuel conducted towards and the oxidizer towards the reaction zone. That is not enough to solve the problem, because what you have here is 1, 2, 3 relations across the reaction. Remember, it's a second order equation, 3 equations, so in principle it's a 6-order system. Of course, it requires boundary conditions, but let's say we know we have those. That's not the issue. But you need enough condition also at the interface, or at the flame surface, or at the reaction zone surface, more accurately. And so you have 1, 2, 3. Those are only 2 relations, because this is one and this is the other one, right? So what you have is 5, it's not enough. But in the infinite chemistry limit, you know that YF is 0 on one side, YO is 0 on the other side, which is in principle 2 more relations. So now you have not 5, 7. Is it too much? No, because also the location of the flame sheet or the reaction sheet need to be determined. So it's a 6-order system plus the unknown reaction sheet, 7 conditions, 7 unknowns. So that's solved the issue. And you have boundary condition, and then that's a summary of what I just said before, okay? With the 2 conditions here. So you can solve, that's what I just said also. And so now you can solve the equation. You see with Lewis number not necessarily equal to 1. This jump gives you a flame location. Note the dependence on the Lewis number, and in fact the Lewis number of the oxidizer. Why the oxidizer play a big role in the flame location? Because this is the reactant that have really to diffuse against the flow to establish the flame location, and it seems like it's the one that affected the flame position. Then you can solve for the temperature. Note that for the temperature, there is no Lewis number, of course, so it's exponentially. And XS is the stoichiometric surface of the location of the reaction sheet. Now I called it stoichiometric. And here is the stoichiometric temperature, which depend on the Lewis number. So unlike premixed flame, where the flame temperature for all Lewis number is the adiabatic flame temperature, the flame temperature of diffusion flame depend on the Lewis number, which means it depends on the way or the means that the fuel and oxidizer are brought together to the reaction zone. This, in fact, was first pointed out in this paper. For unity Lewis number, it reduced to the adiabatic flame temperature as it should. Okay, so we can now generalize this ideas as well. And all I have done here is just express it in dimensional form. So the temperature across the reaction zone, in fact, it can be generalized for not only a planar, but any surface that you like. The temperature mass fraction are conserved or are no jump at the reaction sheet. There is a relation between the fluxes, which we have seen before, and basically this is the statement, the first statement. The net fluxes to the reaction sheet are diffusive. Note that convection doesn't play a role in determining those conditions. That's why it's referred to as a diffusion flame, okay? And the first comment is that the fuel and oxidizer are completely consumed at the reaction sheet, which is the large Damkohler number or the Birch-Schumann idea. For a general surface, the fluxes are along the normal direction to the surface. That's the only difference here. Okay, now let's go to the Birch-Schumann problem, just because it's a curious and nice example, but that's the assumption that Birch and Schumann did. The flow is assumed to be parallel and remain parallel. In other words, not affected by gas expansion and so on. The mass flux in the axial direction is assumed constant. I said that. He assumed that the Lewis number are 1. And moreover, he assumed that you see in the species equation, the Laplacian here does not involve the diffusion in the axial direction. In other words, he assumed that only diffusion occurs only radially, not axially, which can be justified if this is long enough cylinder. Otherwise, there is equal amount of diffusion. That's not in the analysis. And the boundary condition where, as pointed out here, there is only fuel here, no fuel here, only oxidizer here, and so on. By the way, this assumption that diffusion occurs only in the radial direction is actually important, even though it seems like it's a bit hidden. The point here is that this is a parabolic equation, which means that the solution only depends on z from z on, right? From z. If diffusion in the axial direction is included, you have an elliptic equation, and there is what is referred to as upstream influence. In other words, the diffusion can also occur backward up to a certain point, of course, which means that this boundary conditions are not correct, because you cannot prescribe boundary condition if it diffuses further in. So there's something important point to point out. Anyway, so the equations are relatively simple in dimensionless form. They reduce, this is like for the conserved scalar, which is the difference between the fuel and the oxidizer. Well, it's a PDE, can be solved by separation of variable. The only parameter here, phi, is, as I called before, I don't know if I said in words that I will refer to it as the initial mixture strength. Is equivalent to some kind of equivalence ratio, but as I said, there is no equivalence ratio in the fusion flame. So it can be solved by separation of variables, and it's expressed in terms of Bessel function, and the lambda are the eigenvalues when you do the separation of variables, and these are the eigenvalues, so those are numbers that you can determine and so on. But if you assume that YF and Y are equal to 0, which gives you the location of the flame, of the reaction sheet more accurately, then you have a functional dependence between R and Z, right? Function dependence is a surface in this. And if you are interested in the mass fraction, you can easily compute them from this relation, because since psi is the difference in YF and YO, where YF is 0, you get YO, and YO is 0, you get YF. But let's focus on this a little bit. If you just, so it's a just general relation like that. And the flame height can be, well, there can be in fact, two type of solution or that result from this expression that depend on phi, dependent on the mixture, initial mixture strength. One of them that converge toward the center, like the blue curve, and it's referred to over-ventilated. And the other one is under-ventilated, which is the red curve. It depends if you have enough oxidizer or not, it's over or under-ventilated, essentially. And the height, flame height, well, it depends. If it's over-ventilated, the height is determined from this expression where R is equal to 0. R equal to 0 give you an expression for Z, so you get the height. If it's under-ventilated, then you have to set R equal to 1 to get the height H. For example, suppose that you assume that the eigenvalue lambda n becomes, which is true, become larger and larger, so the effect on the exponential is smaller and smaller, and I just keep only two terms in that series, just as an example, then the height can be obtained from these relations, and for the under-ventilated case, I set R equal to 1, R equal to 1, so this is J naught of lambda 1, and this gives you the height from the expression of Z, which is the log of whatever the ratio. And if it's over-ventilated, then you set R equal to 0 and you get the height. And what's interesting is that here is the height. I don't know why it became a capital H, but it's a small h, same thing as capital H. And so it depends on the coefficient of phi, or if you want, depending on C. C was this relative size of the two cylinders, right? The ratio of AB, where A was the radius of the small one, B. So what you see is interesting, that the over-ventilated flame, when you reach that limit, goes like the height go further and further and further. At some point, mathematically go to infinity, where it starts getting the under-ventilated case, okay? Anyway, this is just that. The next thing was the structure of a diffusion flame. So I will finish the Burke-Schumann, and then we'll talk tomorrow about the rest. So the structure of the reaction zone, again, here are the equation. Just a repetition of the previous slides. I put them in dimensionless form, okay? What I'm interested to say is the following. So Burke-Schumann says that there is a sheet where everything gets consumed. But note that the profiles have kinks, have sharp discontinuities. I mentioned to you before that sharp discontinuity is not exactly physically acceptable. In other words, there must be something on a smaller scale that things are more continuous. There is no jumps. And so that's the thin structure of the reaction sheet, the reaction zone. This was only discussed or discovered later, and this is briefly what I want to describe to you. So, as I said, Burke and Schumann introduced the fast chemistry limit as an ad hoc ingenious approximation, but they didn't discuss the structure. The recognition that it's the limit d goes to infinity came much later, and it separate regions where you have convection diffusion from the reaction zone, which have some thickness. And so in the equation outside the reaction zone, the reaction is negligible and is equal to 0, and the limit of large Dam-Kohler number tell you that YF is 0 on this side, YO is 0 here, where this is the fuel stream, this is the oxidizer stream in general picture. And to examine what's going on in the reaction zone, we do a stretching of the coordinate. In other words, we stretch now, since I want to do it in general, we stretch the normal coordinate. We zoom on that region. So how do we zoom? We write n equal to epsilon eta, right? Epsilon is a small parameter. I didn't say what it is yet. So eta will span from, say, negative infinity on the fuel side to positive infinity on the oxidizer side. And when it becomes large and you multiply by epsilon, it means you are a little away from this side and a little away from that side. Okay. So you do the stretching. That tells you d by dn is d by d eta by dn, which is 1 over epsilon. So you put it in this equation where the temperature is perturbed from the flame temperature, or the stoichiometric temperature is tau, and the fuel and oxidizer are perturbed from 0 because they are both consumed. So it's epsilon, epsilon, epsilon. You put it here, and after you also change the coordinate, by the way, the reaction term is going to have an epsilon from the fuel, an epsilon oxidizer. And since there is epsilon here, beta tau, I didn't say anything about theta, then e to the epsilon, e to the 0 is 1. So it doesn't enter the discussion or the picture. So the only thing that you have on the right is the fuel consumption, the oxidizer consumption. And you have here the Dam-Kohler number multiplied by epsilon cubed. So to balance this equation, you have a distinguished limit that determine, or a limit in this that determine how large is the Dam-Kohler number or how narrow is the reaction zone. And so the relation is that the thickness is essentially d to the minus a third. This is a constant, so it doesn't matter, the rho s. Okay, so if that's the thickness of the reaction zone, this is the equation that you have to solve. And you can write similar equation for the fuel and oxidizer. Now they will have Lewis number in them, okay? And have appropriate boundary conditions that come from matching with the outer solution. I explained yesterday in general term what matching is, that the solution has to blend into the solution. It's not what people sometimes call patching. Patching is you patch at a point. In other words, at a given point, the two are the same value. Matching means the solution blend into each other. It's much stronger and more accurate for such analysis. Okay, so the beauty of all this is that no matter what the outer conditions are, you can always recast these previous equations, all these, into one equation that has a very interesting symmetric form. Note that the coordinate here is eta and the function here is tau, for example, and it's going to be by the appropriate scaling. Tau go to some phi and eta to zeta. I didn't write what the transformation is, but you can do a transformation, and it always leads to this boundary value problem, okay? So you have to solve this boundary value problem. It doesn't have any parameters, so you solve it once and for all. And here it is. It's the dashed part. It matched the slopes of, this is for the temperature. The fact that it's symmetric, it's due to this transformation. And so the basic conclusion out of this is that there is a thin reaction zone here that smooth out those discontinuities, and it always exists. So the Birch-Schumann always, this limit has always a solution that is properly defined everywhere, and we know the condition across the sheet, and so we can use it for this large Dam-Coulomb number limit. I think this is, hold on one second. Okay, so what is this? Yeah, okay. So let me just, this is the summary of this. Tomorrow we'll continue. Just to quickly read the summary. Although useful in describing aspect of the fusion flame, the large Dam-Coulomb number does not provide flame extinction. It's known in the fusion flame that when the Dam-Coulomb number is reduced, or when you increase, let's say, the flow rate in that one-dimensional picture, or something else in a different condition, in other words, when the reaction time is not very fast, or the reaction is not very fast. Time is often the opposite, and it's confusing in wording. So when the reaction is not very fast, then the mixing that occurs in that reaction zone is not sufficient to allow for burning, and the flame would extinct, would not exist. This is not seen in that picture. In other words, the large Dam-Coulomb number is always burning. And so this is what we will try to improve tomorrow by considering a distinguished limit in which both the Dam-Coulomb number and the Zeldovich number, or the reaction, the activation energy, are small. Remember that in this analysis, the reaction zone is isothermal. There is no variation, or the chemical reaction rate does not depend on temperature. This is something that we will adjust to accommodate for what I said is missing. And the other comment that were there, what was it? It was first done for a counterflow flame by Lignan in the 74 for unity Lewis number, and it was generalized later on, and so on. So that's sufficient for today. Tomorrow we'll talk about the large activation energy of diffusion and see some examples.